Welcome to the Depth Dive. It is Halloween season, and today we're descending into, well, a different kind of crypt. We're talking about the real horror stories haunting the digital world. Not hackers, not viruses, but something perhaps even scarier. Decay, crushing complexity, and systems that just refuse to die.
hmm We're talking about those sprawling, critical, legacy mainframe systems, the ones still quietly running huge chunks of global finance, healthcare, government.
Absolutely. And these aren't just old, well, they're actively resisting change. They seem almost invincible.
Yeah, developers sometimes call them undead giants. It's quite fitting, actually. They're like digital zombies.
Undead giants, I like that.
And the reason they resist modernization isn't just age. It's the incredible architectural complexity, and maybe even more importantly, the knowledge needed to understand them.
Yeah.
That knowledge is, well, it's vanishing rapidly.
Right? So today, we're diving deep into that alphabet soup of the mainframe. COBOL, JCL, PL1, assembler, the whole lot. We've looked at discussions from expert developers, technical critiques of the code itself, studies on IT project failures, which are shockingly high, and the sheer complexity of data sharing in these environments. Our mission, to give you a kind of shortcut, a map through this terrifying landscape, and maybe reveal the core insight we found. The real problem, the horror, isn't just the code, it's the institutional knowledge, the stuff locked away in people's heads.
Exactly. That knowledge crisis is the frame for this whole challenge. Think about it. These systems, back in 1997, Gartner estimated they ran something like 80% of all business programs worldwide.
80%, that's staggering.
It is, and their persistence shows they're the backbone, the absolute core of critical infrastructure. But trying to modernize them, it often turns into this incredibly risky, unpredictable project.
Why? Because you just don't know what you're getting into.
Precisely. The depth of complexity, the decades of unmanaged technical debt. It's almost impossible to estimate accurately up front. It's a recipe for, well, horror stories.
Okay, let's start with the big one, COBOL. It's almost synonymous with the mainframe era. How on earth did this one language end up running, well, basically everything?
Yeah.
And why is dealing with it today, like you said, digital archaeology?
Well, the irony is it actually started as a stopgap. It was meant to be temporary.
Really? Temporary?
Yeah. The main driver was the U.S. government back in the late 50s. They needed a standardized way to handle data processing across different machines. Portability was the key goal.
Right. COBOL, Common Business-Oriented Language. That effort started in 1959, the Codecil Consortium, and Grace Hopper's earlier work, Flowmatic, was a big influence, wasn't it?
It was. The Department of Defense was the real force behind it. They wanted this common language for business data processing.
But not as a permanent fixture.
No, not really. In fact, some academics were pretty unenthusiastic. There's this anonymous prediction we found from June 1960 saying it was, and I quote, rather unlikely that COBOL will be around by the end of the decade.
Wow, they couldn't have been more wrong.
Couldn't have been more wrong. Because the DoD basically mandated it. They told computer manufacturers, look, if you want our contracts, you need to provide COBOL compilers.
Ah, the power of the purse.
Exactly. And that drove widespread adoption. It got standardized in 1968, and, well, the rest is history.
And that persistence is just mind-boggling. You mentioned the IRS, one of the world's biggest financial entities. They're only now, in 2024, announcing plans to transition some core systems off COBOL and assembler onto Java, 65 years later.
65 years. It's still the bedrock.
But a flawed bedrock, according to critics.
Oh, definitely. Right from the start, there was criticism. The design process itself was apparently messy, lots of discontinuity, lack of talent on the committee, some said. And structurally, well, it lacked support for structured programming early on, which caused issues. Hashtag tag 1.1, the birth of the business language.
Okay, let's talk about that structure. The most famous thing about COBOL is its syntax, right? Trying to be like English.
Yeah, that was the idea. Make it readable for business managers, not just programmers. But the side effect was verbosity. Massive verbosity.
Give us an example.
Sure. So instead of simple symbols like for greater than, you'd literally write out X is greater than Y.
Okay.
Or defining a flag might look like value H to mean, say, wage is hourly. A single line might seem readable.
But multiply that by thousands or millions of lines.
Exactly. You end up with these huge monolithic programs that are incredibly hard to comprehend as a whole, as one source put it, just walls of text.
Which brings us to that famous quote from Edgar Dijkstra back in 75.
Ah, yes. The use of COBOL cripples the mind.
Harsh. But he was talking about that lack of structure, wasn't he? The way logic could just jump all over the place.
He was. That lack of inherent structure makes maintenance today a nightmare. It's hard enough for anyone to read, but for a new developer coming in cold, trying to modify that safely without years of context.
Almost impossible.
Pretty much. #tag 1.2. The technical complexity locked inside.
Okay, so the language itself has issues, but you mention specific technical tricks or features that make migrations hellish. Let's dig into those. First up, the data definition quirk and this picture clause, or PIC.
Right, the picture clause, PIC. This is a perfect example of how deep the coupling is between data structure and the code itself.
How so?
In modern systems, you declare a variable type, like an integer, and maybe the database or the front end handles how it's displayed, right?
Yeah, usually.
In COBOL, you define it right there in the code, PIC 95.
And what does that PIC 95 actually mean?
It means it's exactly 5 digits. If the number is smaller, it gets padded with leading zeros. Want a specific gate format, you might write PIC 99999.
So the slashes, the formatting, it's all defined right there.
Right there. Those slashes are called insertion characters. The presentation logic is embedded in the data definition within the source code.
Okay, I can see how that's a problem for migration. You can't just lift the data.
Exactly. You have to painstakingly find all those PIC clauses, understand the implicit formatting rules, and then re-implement them in your new database schema or your new UI logic. It's tedious, complex, and super easy to mess up.
A foundational headache, indeed. Okay, horror number 2, memory magic with the redefines construct. You said this is where security and debugging go off the rails.
Oh, redefines is something else. It's a throwback to when memory was incredibly scarce and developers used clever tricks.
What does it let you do?
It allows 2 or even more completely different variable names to point to the exact same spot in memory.
The exact same spot.
Yep. So you might define a data structure, say customer record, and then immediately follow it with customer info redefines customer record. Same memory, different names, potentially different implied structures.
We saw that anecdote about the Spanish consultancy. They used it to give Spanish names to variables that already had English names. FONAM and FUTAIL pointing to the same place as the original names.
Exactly, just for their own team's readability. But the original uses were often about saving memory or clever string parsing.
Yeah.
Like one variable holds the whole address, and another redefines part of it to easily grab just the zip code, maybe.
Clever, but sounds like a nightmare for analysis.
It is. Think about static analysis tools. They're automated scanners we rely on today to find bugs or security flaws. They look at the code and try to figure out what's happening. But with redefines, the tool has no reliable way to know which variable name is active in that memory region at any given moment, or what data type it should be holding. Is it customer name? Is it transaction data? It makes finding things like buffer overflows or potential data leaks incredibly difficult without a human expert digging through it line by line.
Yikes. Okay, final technical terror. Control flow confusion with perform THRU. This messes with how programs run.
Big time. Perform THU is COBOL's way of doing subroutines, kind of. It lets you execute a sequence of adjacent code paragraphs, like perform process A, THRU process C.
Okay, sounds straightforward enough.
But here's the kicker. Traditional COBOL often lacks a proper call stack, like modern languages have.
No call stack. So if, let's say, process A calls another perform, how does it know where to come back to?
Well, that's where it gets messy. The system might keep track, but how it does it can vary. If you have nested perform statements, the return addresses can get muddled or even overwritten in some older compiler versions.
Leading to unpredictable results.
Exactly. Undefined behavior. Code that works one way on one machine might behave completely differently or even get stuck in an infinite loop on another. We saw that example where nested perform UU could output 1, 2, 3, end, or just loop printing end, 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 depending on the compiler.
Chaos.
Total chaos for anyone trying to map out the program's logic for a migration. It breaks the standard model of how functions call each other. It's not modular in the way we expect today.
Now, before we get to the modernization failures, we need to address something else. A critique we saw was that focusing only on COBOL misses the bigger picture. There's JCL, PL1, assembler. These other mainframe technologies run by those same vanishing experts.
That's a really crucial point.
Yeah.
Because a mainframe isn't just running COBOL programs in isolation, it's running an entire environment.
And JCL, job control language, is key to that environment.
Absolutely key. Especially for batch processing, which is still huge on mainframes. JCL is basically the operating system scripting language.
So it's not the app logic itself, but the instructions around the app.
Precisely. JCL tells the mainframe what programs to run, when to run them, in what order, what data files they need as input, where to put the output, what to do if a step fails. all of that orchestration.
So like a complex nightly bank reconciliation might involve dozens of COBOL programs.
Mm.
And the JCL script is the master conductor making sure they all run correctly and pass data between each other.
You got it. And often, the JCL is even less documented and more complex and tangled than the COBOL code it's running. Understanding the JCL, those dependencies, that operational flow, that relies almost entirely on the deep knowledge of those mainframe operators and systems programmers. Knowledge that's walking out the door.
Okay, JCL is the conductor. What about assembler? That sounds low level.
It is. Assembler is about as close to the bare metal hardware as you can get in programming. It gives you maximum control, maximum speed.
What dut?
But it's incredibly difficult to write, even harder to read, and almost impossible to port to a different type of machine.
So why use it?
Usually for highly specialized performance-critical routines. Core system utilities, maybe super fast data sorting algorithms, code that needs to directly manipulate hardware features.
And if a modernization team finds a critical piece written in assembler?
It's often a showstopper. You can't just translate assembler automatically. You have to understand the intent behind those low-level instructions, why the original programmer chose to manipulate that specific register or memory location. Often the original programmer is long gone, and their clever trick is completely undocumented. You basically have to reverse engineer the logic and rewrite it from scratch in a modern language, hoping you capture the original function perfectly. It's probably the most terrifying code to encounter in a migration.
So it's not just one language, it's this whole interconnected ecosystem, COBOL for the business rules, JCL orchestrating the jobs, assembler for critical speed tweaks.
And often PL1 as well, another complex procedural language from that era.
Right, and all of it potentially undocumented, all relying on that dwindling pool of experts.
That's the horror story right there. And when organizations do try to tackle this whole tangled mess, well, the results are often pretty grim. That 79% failure rate for application modernization projects we mentioned.
Yeah, that number is stark, 79% fail.
It's critical. Organizations need to really internalize that before they even start thinking about modernization. It means failure isn't the exception, it's statistically the most likely outcome.
Wow. Okay, if failure is the norm, you'd think companies would spend way more time and money just understanding the existing system before even picking a new tech stack.
You'd think so, but often they don't. Let's look at the main ways these things go wrong. The failure modes our sources highlighted. First up is entanglement.
Entanglement sounds messy.
It is. Decades of adding features, fixing bugs, integrating systems, the COBOL code, the JCL, the databases, they all become deeply interwoven, architecturally entangled.
Meaning changing one thing breaks three other things you didn't expect.
Exactly. That's internal lock-in. And then there's external lock-in, where you're totally dependent on maybe one specific vendor who understands a piece of it, or a niche consulting firm with the right aging skill set. Even tiny changes become incredibly risky and unpredictable.
Okay, entanglement. What's next?
Transformation fatigue. This is the human cost. These modernization projects are often massive multi-year slogs.
Right. Years go by.
Years go by, they deliver value in big, infrequent chunks, if at all. Momentum dies. Project sponsors leave. Budgets get slashed halfway through because it's taking too long.
So the team gets demoralized.
Totally demoralized. If it's too slow, people lose focus. If they try to go too fast to compensate, quality drops, burnout happens, stakeholders lose faith, pull the plug, or the project just limps along, never delivering the promised benefits. It just fizzles out.
Sounds exhausting. Then there's talent mismatch. This seems obvious given what we've discussed.
It's huge. You've got your modern teams, skilled in Java, Python, cloud platforms, microservices, and you're asking them to deal with COBOL, JCL, assembler, running on a mainframe architecture they've never seen before. The legacy experts who do understand it are retiring.
So the new team and the old system don't speak the same language, literally or figuratively.
Exactly.
Yeah.
That friction, that knowledge gap, is a massive barrier. The modern team ends up guessing, reverse engineering, making assumptions, which feeds right back into delays, errors, and more cost overruns. It relies entirely on having those application experts available, and they're becoming scarce.
And this risk gets even worse in government, right? That was the fourth failure mode, a 70% failure rate for government IT projects.
Yeah, significantly higher than the private sector average, which is already bad at around 35%.
Why so much worse?
Governments often face unique hurdles. Funding estimates based on, well, overly optimistic historical data. Layers of bureaucracy. Political cycles demanding quick wins from long projects.
So when the project inevitably goes over budget.
The cuts often fall in the non-essential parts. Things like robust testing, security hardening, implementing proper privacy controls. Our sources specifically flag this. Crucial risk mitigations often get dropped or become inoperative due to budget cuts, leaving citizen data or critical functions exposed. It's a major hidden risk. Hashtag tag tag 2.1 the parity trap.
Okay, let's talk about the last failure mode, which sounds really insidious. The parity trap. This is when the goal is just recreating the old system on new tech.
Exactly. This is a huge strategic mistake. The idea is, let's just build exactly what we have now, but using a shiny new technology stack. That way, we minimize business disruption. It sounds safe.
But it's a trap. Why?
Because you're essentially just digitizing bad processes. You're taking potentially decades of inefficient workflows, workarounds, outdated business logic.
Like that example. If the 1970s banking system needed 4 manual steps and 2 manager sign-offs to open an account.
The brand new cloud-native microservices-based system forces the user through the exact same 4 steps and 2 sign-offs. You just, put lipstick on a pig.
So you spend millions, take years, and gain nothing.
Worse than nothing, arguably. Because during that massive multi-year project, the organization is essentially standing still strategically. They're not developing new capabilities, not responding to market changes. They're just focused on recreating the past.
So the end result is a system that's already obsolete.
Pretty much. It's a modern reimagining of what the company needed maybe 3 years ago when the project started. No competitive advantage gained. You just swapped old technical debt for new technical debt, potentially locking in outdated business models.
That phrase, digitization of bad processes, that really hits home.
It should. The real opportunity in legacy modernization isn't just the tech upgrade. It's the chance to fundamentally rethink and streamline the business process first. Simplify the operation, then build the tech to support the simpler, better process.
Otherwise, you just have a faster horse on the same old bumpy road.
Or maybe a fast car driving straight towards a cliff. If you don't fix the underlying process, the new tech might just help you execute bad decisions faster.
This brings us right back to the human element. Why developers joke about needing goat sacrifices and necromancy to update these things? It's all about those vanishing application experts, isn't it?
It absolutely is. This is the bottleneck, the absolute crux of a problem. We saw this again and again in the developer discussions we analyze. They all stress. If you don't have the application experts, those developers, support staff, sysprogs who've lived with the system for years, who hold its secrets, your migration project is, and I quote one, doomed.
Doomed, strong word.
But accurate, I think, because so much critical knowledge simply isn't written down anywhere.
Like what kind of knowledge?
The operational stuff, the why behind the what's, why this particular JCL job runs before that one, why this COBOL program uses that weird redefines trick we talked about. Maybe it was a clever workaround for a bug in an older OS version. The subtle data dependencies between systems that aren't in any official diagram, the undocumented manual procedures needed to recover from certain errors.
It was all just institutional memory, locked in heads.
Exactly. And businesses are, as another source put it, losing human intelligence resources monthly as these experts retire or leave. Every person who walks out the door takes a chunk of that irreplaceable knowledge with them. And that severely limits any effort to analyze, understand, or safely change the system. The challenge isn't just the COBOL syntax, it's the missing context. Hashtag hack 3.1, the documentation vacuum, the data dictionary horror.
Which leads directly to the next horror, the documentation vacuum. Specifically, the lack of a solid data dictionary. This seems like table stakes, but it's often missing.
Oh, completely missing or woefully incomplete in many, many legacy environments. A good data dictionary is foundational. It defines every single data element, what it means, what its format is, PIC clause, how it relates to other data elements, where it's used.
And building one from scratch in these old systems sounds daunting.
Developers described it as hard work with people that are well compensated. And they capitalized hard. It requires intense, dedicated effort. You need to identify every input file, every output file, every database field, every screen element, batch files, real-time feeds, interfaces.
And not just internal stuff, right? You mentioned external integrations.
That adds another layer of complexity. Think about compliance. Insurance companies dealing with ISO standards, banks reporting to federal agencies, healthcare providers meeting HIPAA requirements. All these external bodies dictate specific data formats and reporting needs.
So the data dictionary needs to map the internal COBOL PIC definitions to all those external requirements too.
Absolutely. If you miss something, if you misunderstand how customer postal code defined as POSIM X10 maps to the required federal standard, you risk compliance failures, fines, reputational damage. It's incredibly high stakes.
Okay, so you need the dictionary. But what if you hit the proprietary nightmare? What if the code itself is locked down?
Yeah, that happens. Maybe the original vendor went out of business, or the license agreement forbids sharing the source code with third-party migration teams.
Then what?
Then you're really in trouble. You can't analyze the code directly. You have to resort to, as one developer grimly put it, gathering requirements like peasants.
Meaning?
Meaning sitting down with a few remaining application experts, if you can find them, and just asking them questions. What does this screen do? What happens when I click this buzzer? What report does this batch job produce? Trying to reverse engineer decades of undocumented business logic through interviews. It's incredibly slow, expensive, and prone to missing crucial details. A true nightmare scenario.
Yeah.
Hashtag tag 3.2 AI is a silver bullet, and why it fails.
Okay, so we have a massive knowledge crisis, vanishing experts, missing documentation. Naturally, everyone looks to AI, right? Can't we just point some fancy NLP model at the COBOL code and have it figure everything out, extract the rules, draw the flowcharts?
Well, there's definitely a lot of buzz about that. And effort. Startups are trying to use AI and machine learning to parse COBOL, JCL, etc., visualize the logic, maybe even auto-translate it.
Wow, sense of Buckeye.
But the experienced developers we saw discussing this, highly skeptical. One view was that AI is likely to be an impedance and capable of creating confusion rather than a magic solution.
Impedance and confusion.
Yeah.
Why such pessimism? It's just text, isn't it? Can't AI read text?
You can read the text, sure, but can it understand the context, the intent? Remember those tricks like redefines or obscure JCL parameters?
Oh.
They often exist for reasons tied to the specific hardware, operating system, or even a bug from 40 years ago.
Ah, so a general AI model trained on modern code wouldn't understand why that weird structure exists?
Probably not. It might successfully translate the syntax turn a COBOL ADD A to B giving C into Java's C equals A plus B. But it could completely miss the subtle business logic embedded in how data is structured with picture clauses, or the critical dependency hidden in a perform 3 or year range, or the reason for that assembler routine. It lacks the deep, domain-specific historical context.
So the AI might produce technically correct modern code that is functionally wrong.
Exactly. It could introduce subtle but catastrophic errors, which is why even the companies building these AI tools acknowledge you absolutely need a human-in-the-loop HITL process.
Meaning a human expert has to check the AI's work.
Check it, validate it, correct it, supplement it. The AI can maybe do a first pass, handle some of the grunt work and translation, but a human expert still needs to review it carefully. Raw code conversion just isn't enough.
So success still depends on human expertise.
Absolutely. One team that did successfully migrate COBOL to Oracle BL SQL emphasized it required a very solid understanding of the data model, and a keen eye for detail. And then many parallel test runs with the wide variety of real-world data to prove and benchmark the new software.
The human validation and the testing, that's the real silver bullet, not the AI itself.
Precisely. The AI might be a tool, maybe a helpful one eventually, but it doesn't replace the need for deep human understanding and rigorous testing.
To really drive home the kind of systemic risk we're talking about, the hidden dangers in decades-old code, we have to look back at the biggest collective tech horror story ever. Y2K.
Y2K, yes. It's the perfect case study. A global panic caused by essentially decades of taking a seemingly harmless shortcut.
The shortcut being?
Using 2 digits for the year instead of 4, 98, 99.
Oh, yeah.
Everyone just assumed the century is always 19.
Until a clock ticked over to January 1st, 2000, and suddenly 4 didn't mean 1900. It meant 2000.
Right. And systems that use dates for calculations, interest rates, age verification, scheduling, inventory management, you name it, were predicted to fail spectacularly.
The simplicity of the bug masked the sheer scale of fixing it, didn't it? Because that 2-digit year was everywhere.
Everywhere. Embedded in billions of lines of COBOL, assembler, countless other languages, in data files, databases, hardware chips even. And it wasn't just about the year rolling over. There were those programmer tricks too.
Like using 99 as a special code.
Exactly. Maybe 99 in a date field meant never expires or final record. So when the system date hit 1999, or even tested for 99 before the rollover, things started breaking early. Some systems used 00 to mean ignore this record. These quirks meant failures weren't just theoretical. They were starting to pop up well before the actual millennium. Hashtag 4.1, the scope of the threat.
The fears were apocalyptic, weren't they? Power grids failing, water supplies cut off, planes falling out of the sky, financial markets collapsing.
The predictions were dire, and some of the near misses they found during the massive remediation effort show it wasn't all hype.
Like the missile system?
Yeah, in the UK, they found the Rapier anti-aircraft missile system had a flaw deep inside the field equipment. On January 1st, 2000, it just wouldn't have been able to activate the missiles. Completely useless.
Wow.
And the U.S. Coast Guard found bugs that could have caused ships to lose steering control. Imagine container ships drifting uncontrollably in busy ports. Catastrophic potential.
And the actual failures, even if less dramatic, were sometimes just bizarre. Tell us the video store story again.
Oh, right. The store in New York State. Their system apparently calculated that a movie return in early 2000 had been rented for 100 years, and it tried to charge the customer something like $91,250.
Incredible.
Or the court in South Korea that automatically sent out summonses for people who appear on January 4th, 1900. And there were real operational impacts, too. That Chrysler assembly plant that tested its systems. The security doors immediately malfunctioned, locking everyone in or out. Even the fancy new Millennium Dome in London, its systems threw up so many Y2K errors during testing. The error messages literally scrolled off the screen faster than anyone could read them. It just showed the depth of the problem. Hashtag tag 4.2 the solution and its new risk.
So disaster was mostly averted. How? What was the main fix they deployed globally?
The most common solution, largely because it was faster and cheaper than fixing every single date field everywhere, was called windowing.
Windowing. Sounds like a patch, not a real fix.
It absolutely was. It was the pragmatic choice, but it basically kicked the can down the road.
How did it work?
Instead of changing the data to store 4-digit years, which would have required massive data conversion efforts, windowing kept the 2-digit years, but changed the program logic. The code was modified to infer the century based on a sliding window.
For example,
the code might say, if the 2-digit year is between 000 and, say, 19, assume the century is 2000. If it's between 20 and 99, assume the century is 1900.
Okay, so 05 becomes 2005, and 85 becomes 1985.
Exactly. But here's the problem. Every organization, every system, potentially chose a different window. Maybe one system used 0029 as the 21st century, another used 0049.
Uh-oh. So if those systems needed to exchange data?
Major coordination headaches. Ensuring everyone in your supply chain, all your partners, were using compatible windows was a huge effort.
Right.
But that wasn't the worst part.
What was the worst part?
The window has an end date. That pivot year, the 19 or 29 or 49 in our examples, is just the next Y2K cliff edge for that specific system.
So it wasn't a permanent fix at all?
Not even close. It just bought time. And the truly scary thing is, nobody has a complete inventory today of how many critical systems are still out there running on windowing logic with their own specific window expiration date looming.
They're just ticking time bombs, waiting for their own little Y2K event when, say, the year hits 2030 or 2050.
Precisely. We averted the big crisis in 2000, but we may have sown the seeds for countless smaller, harder-to-predict failures in the future.
And the cost of Y2K remediation was astronomical, wasn't it? Estimates were like $300 billion to $500 billion globally.
Huge numbers.
Yeah.
But interestingly, there was a hidden silver lining to spending all that money.
Oh, what was that?
Companies were forced to do a deep inventory of their IT systems. Many, for the first time ever, got a comprehensive picture of what software and hardware they actually had. And boards of directors suddenly woke up at how critical and how risky IT infrastructure really was.
So Y2K, despite the cost and panic, actually improved IT governance in the long run.
In many ways, yes. It was an incredibly expensive but ultimately necessary lesson for the business world about managing technical debt. And those deep-seated problems in legacy code, the rigidity of COBOL data structures, the tangled mess of JCL, they really come home to roost when you look at large-scale government initiatives. Things like data sharing, service integration, modernization across agencies.
Right. The political goal is often efficiency, joined-up government, providing seamless services to citizens. But the technical reality hits that barrier of data silos.
Hits it hard. Mainframe systems, with their fixed data formats and batch processing origins, are just inherently difficult to merge, as one study put it.
But it's not just the tech, is it? You mentioned organizational barriers, too.
Often, those are even bigger hurdles. Different agencies, different departments. They might have incompatible hardware, sure, but the real blocks are often cultural and political.
Like lack of trust?
Lack of trust between institutions is huge. Agencies fiercely protect their data, their turf. They worry that sharing data means losing control, losing budget, losing influence over their specific mission. Data becomes a political asset.
We saw that example from the UK's joined-up government push after 1997. The idea was sound centralized, save money, improve services.
But the reality was chaos. The projects became incredibly complex, bogged down by trying to integrate incompatible legacy systems and navigate those intense turf wars between departments. The result? Major and expensive IT failures. And enthusiasm for the whole concept just evaporated. The organizational resistance proved just as intractable as the technical debt.
And in places with multiple layers of government, like federal and provincial systems?
Even harder, aligning priorities, budgets, and deeply entrenched aging systems across different levels of bureaucracy, it makes large-scale integration incredibly vulnerable to failure. The technology choice almost becomes secondary to the political and organizational challenges.
Okay, so let's say somehow, despite the odds, organizations do manage to break down some silos and integrate data from these old systems. Then they face another insidious risk: function creep.
This is a really strong tendency. Once data is collected and made available for one specific purpose, there's immense pressure to start using it for other unrelated purposes.
The WHOIS directory for domain names is a classic example, right?
Perfect example. It started as a simple technical tool. Find the contact person if a domain name is causing technical problems. Purely operational.
But then,
law enforcement wanted access for investigations. Intellectual property lawyers wanted it to chase trademark infringement. Marketers wanted it for contact lists. The scope just kept creeping outwards.
so the data disclosure requirements ballooned far beyond the original purpose.
Way beyond. And often, that creep directly conflicts with basic data protection principles, like purpose limitation, only using data for the reason it was collected. But once the database exists and the access mechanisms are built, it's very hard to put the genie back in the bottle.
Which leads to the data retention horror. Even if the original need passes, the data sticks around, like that Fi-In Traxi case in Canada.
Right, the Financial Transactions and Reports Analysis Center. They track financial data to detect money laundering and terrorist financing.
Yeah.
A vital mission. They argued they needed to keep data longer to spot complex patterns over time. Fair enough. But multiple audits by Canada's Privacy Commissioner found they were consistently retaining too much data, holding on to information beyond what was necessary or legally justified.
Even after being told to stop.
Even after audits flagged it. It just shows how hard it is to reverse data accumulation once the systems and processes are built to hold on to it. The bureaucratic inertia, the technical infrastructure itself, encourages keeping data just in case, regardless of the original justification or privacy rules.
And when you combine this data accumulation with the opacity of the old systems, the undocumented logic, it raises huge questions about fairness, doesn't it? Especially when decisions affecting individuals are being made.
Absolutely critical questions. Procedural fairness and due process become paramount.
That U.S. computer matching example was interesting. Agencies swapping tapes of citizen data to check eligibility for benefits.
Yes. And the research found that simple administrative rules or cost-benefit analyses didn't really stop potentially unfair or inaccurate matches. What did work better was enforcing due process.
Meaning the citizen had a right to know what data was being used and challenge it before their benefits got cut off.
Exactly. Giving the individual a chance to see the information, contest errors, and have their case reviewed before an adverse decision was made based on potentially flawed, opaque data matching from legacy systems. It's about basic fairness.
So any big modernization or data sharing project, especially in government, doesn't just need to be technically sound or legally compliant.
It also has to pass the ethical smell test. Is it fundamentally fair to the people whose data is involved? And the inherent inflexibility and lack of transparency in many legacy systems make guaranteeing that fairness a massive challenge.
It really drives home the point. Modernizing these behemoths isn't just a tech project. It's strategic, it's organizational, it's political, it's ethical, and the ghosts of decades-old decisions embedded in that code can haunt the entire process. #outro. Well, we have surfaced, blinking from the depths of the mainframe crypt. We took a deep dive into the real horror stories of legacy IT. Let's quickly recap the main nightmares we uncovered.
Okay, so first there's the deep, almost terrifying technical complexity of the legacy code itself. We're talking COBOL, yes, but also the whole ecosystem. The JCL orchestrating everything, the assembler for those critical, scary bits.
And those specific quirks like redefines letting variables share memory in confusing ways or perform THRU messing with the program flow.
Yeah.
Things that just break modern analysis tools.
Exactly. That's horror number one.
Horror number two.
Yeah.
The sheer strategic nightmare of the high failure rate. That 79% figure is chilling. Driven by organizational problems, the soul-crushing transformation fatigue on long projects. And that awful parity trap, spending millions just to perfectly recreate your outdated processes on new technology, digitizing the bad stuff.
A guaranteed path to obsolescence. And then, maybe the biggest horror of all, the knowledge crisis.
Right. The total dependency on those vanishing application experts, the people who hold the keys, the context, the why behind the code.
And the related documentation vacuum, especially the missing data dictionaries. Without that knowledge, without that documentation, you're flying blind when you try to change anything. The system's secrets are locked away, and the people with the keys are leaving.
So the synthesis here, the big takeaway, it seems to be that the sheer tangled complexity of these decades-old systems means the effort needed to modernize them is almost always vastly underestimated,
By management, by leadership, by everyone involved who hasn't lived in those trenches.
leading inevitably to budget overruns, missed deadlines, and outright failure. The application experts, the ones who understand the crypt's layout, they hold all the power.
They really do. Which brings us to our final, maybe provocative thought for you to chew on.
Okay, let's hear it.
We saw with Y2K that when the world faced a massive, unavoidable crisis, forcing everyone to fix their legacy code, some good things actually came out of it. Better IT inventories, better governance, boards finally paying attention.
The silver lining.
Right. But if that immediate burning platform pressure, like Y2K, or maybe a huge regulatory change isn't there, why would a rational organization take on the massive risk and expense of a full-blown mainframe modernization, knowing that statistically it's far more likely to fail than succeed?
That's a good question. Inertia is powerful.
It is. So the truly terrifying question, maybe the real ghost in the machine for Halloween, is this. What specific ticking time bomb, a flawed JCL procedure, a forgotten windowing fix about to expire, a subtle bug introduced by a redefined interaction is lurking right now in the shadows of a critical COBOL or assembler module?
That we won't know about.
Until its own unexpected turnover day arrives and something vital simply stops working. What's the next Y2K hiding in plain sight within these undead giants?